In this video, we are going to talk about how we can protect foundations, and we are going to cover slab on grade. We will take a look at how we can do the basement floor, and we are going to examine the protection against water damage and heat transfer in buildings with a basement floor, how we can, without the basement floor, sorry, how we can do this on sloping sides, and how to do the crawl spaces. Also, we will examine the same protection against water and heat in buildings with a basement floor. And we will take a look at how we can do the areaways. The last topic will be how we can protect the buildings against seismic activity. Let's start with the components of the foundations. In fact, this is just the summary of what we have learned lately. Let's remember the components of the foundation. Uh, we start with the building. We make these decisions about the envelope, its outer surfaces, its geometrical form, its location, and all these decisions will be used as a base for our next set of decisions for the units. These will be the living spaces for the user. Our main purpose is to provide protection for our user against all these negative features like negative air conditions, heat transfer, noise, sort of things. And with these units, we are providing specific functions such as preparing food, like kitchen, or sleeping, like bedroom. All these units, semi-closed spaces, closed areas, and open spaces, will be created with elements, and all that protection, plus additional functions like preparing food or sleeping will be again provided by the elements. These are the integral products, and we can form them by combining the materials, pieces, and components, so that we can physically meet one or some of the functions of the buildings. We have elements like walls, roof, floors, and each one will serve for different purposes in order to meet all these functions. And when we start constructing the building, each piece and component will create certain loads. These can be vertical loads, or based on our location, there will be environmental factors like earthquake or wind. These will create lateral loads. Loads will be carried by a system. Also, this system will work to keep the form intact. This will take all the loads, carry them, and transfer them safely to the ground. This is what we call a building structure. The building structure needs to be integrated with the floor component, the body part of the floor and the roofs, because this is where all the loads start. The weight of all the components of the roof and weight of all the people and the furniture and everything, other layers over the floor, will be transferred to the horizontal components of the building structure, beams. Each beam will transfer their loads to the vertical components, columns. Uh, so we have another system so that we can safely transfer all these combined loads to the ground. Uh, that's where the foundation come into play. This element will support the superstructure. It will transmit all the loads to the ground. Ground is the soil that we construct our buildings on top of it, that soil. Uh, and we need to anchor the building, the superstructure, to the ground safely. Uh, all these three main functions will be executed by foundations. Generally, we don't see it because it's buried inside the ground, and it will look something like that. This is the floor. These are the columns, the building structure. In skeletal structures, the walls, they don't do any carrying uh, function. They are just for separation, so we can take them out for a while, for now. Then we will have the superstructure with the beams and the columns. Uh, each column of the superstructure needs to continue towards the earth as a foundation column. And these foundation columns cannot be smaller than the columns of the superstructure. But first, we need to do the excavation because we need to go deeper inside the earth in order to anchor the superstructure. So first we need to excavate the earth. That's our excavation pit. Uh, Now we can construct single pad footings, uh, and over them there will be reinforced concrete foundation columns. And since we don't want them to be separated like that, because it will be dangerous in terms of load transfer and earthquake risks, we want to combine them to each other. On footing level, we can use reinforced concrete tie beams, so the footings will be combined. And on grade level, we can use grade beams to combine these four separate columns together. So that's our foundation, four main components. But we should always keep in mind, in earthquake-prone zones, this type of separate footing, single pad footings, even if they are combined with tie beams and grade beams, uh, it shouldn't be preferred uh, because uh, the system will be weak against lateral loads. And based on the properties of the ground, the grains, we can change the type of the foundation and create something more uh, stronger. Uh, if we keep continuing one of the footings towards a certain direction, we will have a continuous footing. That can be imagined as a long footing, just one long footing, and there will be two columns or more columns on above this footing. So we can have a continuous footing in one direction. That's what we call a one-way continuous footing. Or if we want, we can do this in two directions, and it will be two-way continuous footing. Uh, that's the one-way continuous. So we create a long footing in one certain direction, and there will be foundation columns, two or more foundation columns over one footing. However, since these are still separated in the other direction, I need tie beams to connect them to each other. And I still need grade beams to connect these four separate columns together. So that's one-way continuous footing. And if we want, we can create this two-way continuous footing. It's just one long, continuous, and closed footing with four columns or more columns on top of it. Since we have only one footing, one long and continuous and closed footing, there is no need for tie beams anymore because there is nothing to tie. However, we still have four separate columns. That means we need grade beams to connect all these columns together. Uh, this is a better foundation in terms of load transfer because we are creating a larger footing. That means that all the loads will be distributed in a better way. So if the bearing capacity of the ground is not enough, then we can prefer either one-way or two-way continuous footings. And since the footings are one big object, it will be better for us to avoid the risks of lateral forces, earthquake forces. However, there can be some circumstances, certain circumstances that even that continuous footing is not enough for us. In those conditions, we can prefer raft foundation. First, we need to do a little bit excavation because the thickness of the raft foundation is larger than the height of the footings. So I excavated a little deeper, and here I will create one slab, a thick reinforced concrete slab. Uh, On top of it, I can have my foundation columns and connect them with grade beams. Uh, and that will be better for us to transfer all the loads. And if there is the water, groundwater, with this thick and heavy slab, I will be um, in a better position against the buoyancy of the water. And that's how we can do the shallow foundations with four different alternatives. Uh, we need an appropriate surface for the ground floor because as we finish the construction of the foundations, we are going to put all the earth back and we need a surface for our ground floor. Uh, Here we can use slab on grade. Otherwise, there is no place for users to stand on the ground floor. We need a solid, smooth surface, something like this. And it doesn't necessarily have to be in the indoor area. We can create this same surface in the outdoor area as a terrace area. Uh, and that's called slab on grade. Uh, Here, that's our foundation. It's completed. We are at the grade level now. And the first thing that we need to do is put all the earth back and bury the components, both inside the building area and outside the area. So there won't be any gaps, excavation gaps. Everything will be filled. And as you can see, they are buried inside the earth. Only this certain height of the grade beams, they are visible now. And we are going to fill this part with certain things so that they will be at the same level and that will create our ground floor. But first we need to compress the earth. With a heavy object because as we excavated the earth, all these grains they moved, and when we put them back, there are more gaps in between them. So we need to compress them, get rid of all these gaps. Otherwise, as we apply more loads, as we apply building products, and as we put the people in, that means that the load will be increased. The grains will be compressed at that time, and that can be dangerous. So we first compress it with certain devices, heavy devices. These can be machines like that or objects like this, uh, something like that. So all the grains will be compressed together, and over this compressed surface, we can put gravel. Gravel for 15 centimeters. That's how we can fill these inside surfaces with gravel, but there is still a gap, a level difference between the upper surface of the gravel and the upper surface of the grade beams. For that gap, we can pour concrete without reinforcement bars, only concrete for 10 centimeters. As we do that, the level difference will be equalized, and the upper surface of this uh, concrete will be at the same level with the upper surface of the reinforced concrete grade beams. This is only concrete, and these are reinforced concrete, so they are not the same material. There is this difference of reinforcement bars, but they will be all at the same level, and this is what we call slab on grade. The combination of 15 centimeter thick gravel and 10 centimeter thick concrete will create our ground floor. In Turkish, we call it toprağa oturan döşeme. Toprağa oturan döşeme. Okay, I'm going to write it. Toprağa oturan döşeme because this floor made out of gravel and concrete is placed right above the compressed earth. That's what we call why we call it toprağın döşeme. And there is a reason for us to put gravel over the compressed earth. And so this is the upper surface of the earth, and it's compressed now. It's smooth, and as you know, earth ground is the granular porous substance that can include different grain size. The bigger one is called gravel, the smaller is the sand, and then there's silt and clay, four different grain size. And why do we need 15 centimeter thick gravel over this mixture of different grain sizes? There can be gravel also. There's a reason for that. If we place these crushed stones of gravel for 15 centimeters over the surface of this mixture. This height is 15 centimeters. Then when we pour concrete over the gravel, uh, for 10 centimeters, that will be another 10 centimeters for the height. This concrete will penetrate inside these uh, pieces of gravel so that that gravel will provide us with an increased surface area, and so that the concrete will be attached to the surface of the earth in a better way with this increased area. That's why we prefer that. Okay, let's move on. Uh, that's slab on grade, and as you know, this building it doesn't have a basement floor. It starts with the ground floor directly, and it has a foundation that is deep enough so that the building will securely be anchored to the ground, and there is no risk of frost by putting the foundations below the frost line. So this depth is not for a basement. It's not appropriate for a basement, and there is no place for a basement. But what happens if we need a basement floor? How we can provide living spaces under the ground? That's what we call a basement floor, bodrum kat in Turkish. This building, it's a building without a basement, and we can create the same building with a basement, but first, we need to excavate deeper than the first alternative because we need a higher space here so that people can be in there. It needs to be at least 2 meters, 70 centimeters, 2 meters, 80 centimeters, or even 3 meters or more. Uh, that means that we first need to excavate deeper, and then we can construct the footings, and over the footings we can construct our foundation columns. In normal conditions, this is what we need to do. We need to combine the foundation columns with grade beams. But in this case, if we have columns and beams, and there are gaps in between them, and when we place our ground floor over that, these gaps will provide us to create that basement space because we are going to put the earth back, and we need surfaces between these columns and beams to prevent the earth to be inside this gap, inside this space. So we can prefer brick walls. But as you can easily understand, when we place brick walls here in between these columns, so that we can have an empty area in the inside of this uh, part for our basement floor. But when we try to put all the earth back to this pit, the earth will create a certain amount of load, lateral load, pressure. And these brick walls, they won't hold it because they are not strong enough. They don't have the capacity to carry all that load. So it will be inappropriate. They will crash down. So we need something stronger. Uh, Instead of creating different columns in the outer surface of this basement floor and placing a reinforced concrete floor slab on top of it, we can create shear walls, not separate columns and beams, but a shear wall. Here, if we create a shear wall, the whole reinforced concrete shear wall will be carrying all the loads. It's something like a long, big column. So we don't need separate columns. We don't need to combine them with beams because it's just one load-bearing surface. It's something like this. In the frame system, I create one column and I connect it with the other column with a reinforced concrete beam uh, like this here. Uh, and that's what we call a frame. And it can continue in this direction as well. I can create one more beam to connect it with the other column here, like this. This frame will go like that. And if I want to create an indoor area here, then I need surfaces. I can either create walls out of brick or some other materials here in between these columns and beams so that I will be separating this indoor area. This will be the indoor area, either in the basement floor or in the ground floor or in the first floor. It doesn't matter, from the outdoor area. However, in the basement floor, because we are going to put all the earth back and there will be pressure of the earth and the water, these walls will not be strong enough to carry all the loads. So instead of this separate column, beam, column frame, we can create just one load-bearing big wall. That will be the shear wall, a big, long column like this. So I won't be needing any beams or columns because the whole surface is load bearing now. And if I want, I can continue it towards this direction like that. So there will be one more shear wall. And in normal conditions, this is how we do that. We cast the reinforced concrete floor slab with the beams like this. So if I just have a section, it will look like that, right? It's the beam and floor. Floor is 10 centimeters and beams, they have a certain height. This is what the section look like. This time, since there is no separate beams and columns, I can just attach the floor slab directly right on the uh, shear walls uh, and make them carry the loads of the floor. So that's the section of the shear wall, like that. Sorry about my drawing. And there will be just one floor slab for 10 or 15 centimeters, like this. Uh, And so all this surface will be load bearing and it's just one material. It's just reinforced concrete. There shouldn't be any lines like that. We shouldn't make a drawing like this. Okay, these are wrong because it's the same material. There shouldn't be any lines there. Uh, so that's it. So the loads of the floor will be directly transferred through these shear walls. There's no need for us to, apply the loads to the beams and the beams will transfer them to the columns anymore because it's just one single surface. That's how we can create the uh, basement floor. And over that, we can place our beams and the floor slab like that. So that will be the basement floor. And as you can see, instead of gravel and concrete to create that slab on grade, we can have directly reinforced concrete floor slab, uh, as we learned previously. That's the basement floor. So let's take a look at the buildings without a basement floor, how we can protect the foundations. Uh, we have these different components for the foundations. Either without the basement floor, we have columns, reinforced concrete columns, footings, uh, reinforced concrete beams, and with the buildings basement with a basement floor, we will have shear walls, again made out of reinforced concrete. All these components, they are the combination of concrete and steel, and the steel material, it's converted into these steel reinforcement bars. And we know that concrete is a porous material. It has holes, lots of holes inside. That means that it's the opposite of non-porous materials such as glass or steel. There are no gaps. Non-porous, no gaps means that there is no void for water to penetrate inside. However, it's not like that in concrete. If there are gaps, open gaps, then the water will penetrate inside the concrete. And if it reaches and touches the steel bars, then they will all be corroded. That's something that we need to avoid. That's we don't want that, and that water can penetrate through all these surfaces, from the sides, from the upper surface, from the lower surface. Every surface will be a way for the water to enter through the steel bars. And we don't want that. It's very dangerous for reinforced concrete buildings. As you can see here, the superstructure, it's almost intact. There's no damage with the superstructure. However, the parts, the ground floor, basement floor, those parts where the building meets with the damp earth, with the water, it's damaged. It can be a big problem during the earthquake. Uh, if we can prevent the water to penetrate the concrete, then there will be lesser risk for the steel reinforcement bars to corrode. There's a lesser risk, lower risk of corrosion. And Here, we place, if the building doesn't have a basement floor, we just place gravel and concrete as the slab on grade as our ground floor surface. And We know that there is a risk of capillarity. Capillarity means kılcallık or capillarity in Turkish, the same word. Water can go upwards against the gravity through those little pores, little gaps. Uh, if the water will go upwards, then these upper surface of the ground floor and these walls will all get wet, and this is something bad for the users. We need to protect the building material itself, reinforced concrete columns, beams, footings, and shear walls themselves, because if we don't protect them, there's a risk of corrosion and it will be dangerous in terms of structural stability. Also, we need to protect the space itself and the user. We need to provide them both protection for the building products, components, and the space user itself. Uh, that means that we need to provide insulation against water damage. We need to provide insulation against heat transfer. Let's first examine how we can do that in a building without a basement floor. Here we will have separate columns, either single pad footing or continuous footing, it doesn't matter. We will have footings, we will have beams and tie beams and grade beams, and all these components will be buried inside damp earth. and there will be water all over these surfaces, over them, in on sides, under them. Everything will be covered with either water or humid earth. So there are lots of risk of water penetrating through all these surfaces. How we can prevent the water to penetrate inside this surface? We need a barrier throughout all these outer surfaces. Uh, in order to waterproof all these surfaces of columns and footings and tie beams and grate beams, we can either cover them with certain products which do not let water pass through, such as these products can be in the form of membranes or sheets, örtü, membran, örtü, or they can be in the form of paste, such as plaster. It's half liquid, half solid, in the form of paste, like sıva, plaster sıva. And we apply them with a trowel. That device is called a trowel, mala. Or it can be in the form of liquid, such as paints. In those conditions, we can apply them spraying over these surfaces, or we can use different types of brushes, either rollers or standard brushes, to paint all these surfaces. The plaster has a certain thickness. It can be half of a centimeter, 1 centimeter, 1.5 centimeter, 2 centimeters, even 3 centimeters. But paints, they are very thin. They don't even have 1 millimeter thickness. It's thinner than that. It's mostly in micron level. It's very thin. It's just a film, something like a film over the surface. But if we apply plasters or paints over these reinforced concrete surfaces, we know that concrete can have cracks. These cracks can be because of heat differences. If we heat the concrete and then let it cool, uh, then because of these heat differences, the concrete will first expand and then contradict, so that all these volumetric changes may end up with cracks. These cracks can be on the surface, tiny little cracks, or they can be structural cracks, important cracks, or these cracks can be because of earthquakes, even if the building structure is intact. With little earthquakes, there can be again surface cracks, tiny, non-structural, non-important cracks. However, with these surface cracks, the plaster or the paint, since they are very thin, will crack as well. Uh, that means that with the cracks, there will be voids, a passage for the water towards the inside, towards the reinforcement bars. Again, there will be risk of corrosion. Uh, then we can prefer membranes, but as you can easily understand, there are lots of surfaces, 4 sides for the columns, 6 sides for the footings, and 4 sides with the beams, lots of surfaces, and it will be very hard for the workers to cut all these membranes and place them over these surfaces. Even if they manage that, there will be, like I covered this surface with one membrane, then okay, this is now waterproof. The membrane won't let the water pass through. And I'm going to cover the other surface with a new membrane. Then this will be again waterproofed. It won't let the water pass through. However, what about the joints? That line that these two different membranes meet, there is a risk of leakage. Throughout that line, water can penetrate inside, and with the single pad footing, one-way continuous footing, or two-way continuous footing, even the raft foundation, There will be lots of different joints. The more the joints, the higher the risk. So we don't want that. We need to look for an easier solution. Because there are lots of surfaces, it will be hard for workers to cut all these surfaces, and it will be expensive. Uh, as well. So can we find a better and easier solution? Instead of trying to cover the surfaces with membranes or liquid or paste products, we can try to produce the concrete without the pores or without open pores. Uh, if we can find a way to fill all these pores, then the concrete will be a non-porous substance without any voids. There is no risk of water penetrating towards the uh, reinforcement bars, or we can have still pores, but this time they will be closed pores. They are not open to the outside environment. With the pores, the concrete will be lighter, but since the pores are closed, again, there is no way water can penetrate inside, and we can use admixtures, certain chemical compounds that we can have as a mixture, as a substance in the mixture of the concrete. These can be, again, in liquid form or in powder form. Uh, these are called waterproofing admixtures, su geçirimsizlik katkıları in Turkish. Su geçirimsizlik katkıları. This is what we call them. And here, uh, these are mostly chemical substances, either hydrocarbon resins, hydrocarbon rechine. Uh, and these are certain things that are manufactured in factories, certain chemical compositions, or we can use coal tar pitch, kömür katranı zifi. And if we mix them in the concrete mixture, then we will either have a concrete that doesn't have any pores, non-porous concrete, or we can still have pores, but they will be closed, so the risk of water penetration will be minimum. So we can prefer them. And if we have concrete with waterproofing admixtures, then all the reinforced concrete components, the columns, footings, tie beams, and grade beams, will be waterproofed. We don't need to do anything else. But how about heat insulation? We learned that there is this level, if as we go deeper and deeper inside the earth, there is a level, and below that level, the temperature is constant. It doesn't get cold or hot anymore because that height, that thickness of earth will provide heat insulation. That's where we place our footings, that the level of frost line. So we can make sure that under this level there is no heat transfer, but above that level there will be heat transfer. That means that soil above this line gets cold or hot depending on the climate. If it's the winter time, then we will have a heat transfer here at this level of the earth. It will get cold. If it's summertime, then it will get hot. Concrete, steel, and glass, these materials are very compact materials. Compact means they transfer the heat very quickly. Just in this example, you can see easily there is a heat source, boiling water. It's very hot. And someone did this experiment. There are three different materials: wooden spoon, metal spoon, and plastic spoon. They place a piece of butter on each spoon, and the other ends of the spoons are dipped into the hot boiling water. Since metal is a compact material, it transfers the heat very quickly, so that the heat is transferred through this metal spoon. It caused the butter to melt. However, since wood has lots of voids inside it. It means that there are air gaps. Uh, it prevents the heat to be transferred very quickly. It slows down the transfer. It creates some sort of heat insulation. That's why this butter is still in its solid form. It's not melted like the one on the metal spoon. Uh, we need to slow down the heat transfer in concrete. The heat is transferred through molecules. The compact the molecules, the quicker the heat transfer will be. Uh, Here, if it's -10 and we want to keep inside this ground floor and first floor, if you have a basement floor, that floor as well, warm, that's +20. And here it's probably -1, that's probably 0 or 2 centigrade Celsius. So it's colder than this inside area. That means that this ground floor, all the heat will be transferred through the cold earth and then the outside environment. We will lose heat. And this is something that we need to avoid. We want to keep indoor area warm and we don't want heat to be lost. That will be both economically and in health-wise a problem. Uh, it will be the same during the summertime. It's very hot outside, and we want to keep indoor area cool. You know that the heat is always transferred through the high temperature area to the low temperature area. So this time, the upper surface of the earth will be hotter than the indoor area, so that the heat will be transferring through this hot earth, hot soil, towards the inside area, and we are trying to keep the indoor area cool by with our air conditioning devices, electrical devices. Again, it will cost us lots of money, and it's bad for the environment. So we need to provide heat insulation for our foundations, but only for the components above the frost line, because we know that under this frost line there is no heat transfer. So we don't need to provide heat insulation for our footings, but or the tie beams, but everything above the frost line, our columns and grate beams needs heat insulation. Uh, we can cover them with a proper heat insulation material. As I told you, we don't need to cover the footings and the tie beams with heat insulation materials because since they are under the frost line, frost depth, there is no risk of heat transfer. Uh, so the covering the foundation columns and grade beams will be enough for us. And for a proper heat insulation material, we are looking for something thick, something has lots of gaps inside it, and in those gaps, there is this air trapped. It's the same principle with our jumpers. We wear jumpers during the winter time, and inside these fibers, wool fibers, there are lots of trapped air molecules. Trapped air molecules will provide heat transfer. We will provide heat insulation. That means that our skin surface, it's hot. The outside air, it's cold. So the heat wants to go towards from the hot side towards the cold side. And by placing this barrier of wool with lots of trapped air molecules inside it, we slow this transfer from our skin surface towards the cold outside air. So we can use the same principle for our buildings. We have certain heat insulation materials. This is glass wool. It's yellowish color, lighter color. And we have rock wool. They are very similar to each other. They are like very thick blankets, like 5 centimeter thick blankets, and they are very lightweight. and they're actually made out of glass or rocks. We have these volcanic rocks, and in factories, they create very tiny, very light fibers out of these glass or rock material. They gather all these fibers together and they compress them into these uh, boards. There are lots of gaps inside these fibers, and in those gaps there is lots of air trapped, and it's very very soft. You can easily squish it with your fingers like that, and these materials are very good against fire, since they are made out of glass and rock. They don't get they are not flammable, they are non-flammable, and you cannot burn them. They resist fire. They provide a very high level of heat insulation, but they are very weak against water. If they get wet, all these gaps between these fires will be filled with water, and they will get very heavy, like when you are washing your carpets, the dry carpets, you can hold them, you can carry them, but as the carpets get wet, they become very heavy because they will hold lots of water, and it makes them very heavy. And since the gaps are filled with water now, they start to transfer the heat quicker. So we don't want them wet. We need to keep them away from water. Uh, as an alternative, we have EPS or XPS. As you remember, these are plastic materials, a certain type of plastic. We have styrene. It's a chemical substance, the combination of these atoms. And we have, if we just combine these atoms, we have a monomer, only one molecule of styrene. Uh, and we can multiply it into a chain. That's what we call a polymerization. Uh, since we have monomer, it's a single molecule. If we polymerize, multiply this single molecule, then we will have a strand polymer. Poly means multiple in Latin, as you know. So it's a chain of lots of strand monomers. It's a polymer now. And we can have one molecule, we can gain certain heat, and it will expand. If we get all these expand bubbles into this board, then we will have EPS, expanded polystyrene, or we can force that plastic substance through a gap, certain gap, that in that time we don't have these air bubble like things, and we will have XPS, extruded. That's extrusion. The process is named extrusion. That's why we call it extruded polystyrene. And these materials, they have a better strength against loads. It's you cannot easily crash them like you squeeze them the glass wool or rock wool. They will hold against loads in a better way, but they are very flammable. Since they are plastic, they can easily get burned. So fire is a very high risk in terms of plastic materials, and they won't be affected against water damage. Here we have bubbles, but they are tightly compressed to each other in this board form. But in the extruded form, there's no gap. So no gap means there's no place for water to penetrate, and they won't get ruined in water. So water is not a problem here. These are different alternatives: glass wool, rock wool, EPS, XPS. Let's compare them so that we can find a proper heat insulation material for the foundations. First of all, heat insulation level, it needs to be high because that's our main goal here, to prevent heat to leak. We want to slow the heat transfer down. We know that glass wool, rock wool, its heat insulation level is very high. Uh, just like EPS and XPS, they provide a high level of heat insulation as well. Fire resistance, it's very good. They're inflammable, incombustible. But EPS and XPS, they are very bad. We shouldn't use in the risk of fire. We shouldn't prefer them. Water resistance, these are bad. They will be filled with water. They will get very heavy and they will lose all heat insulation properties. And these are good, no gaps, no water damage. Pressure resistance, again, these are bad. You can easily squeeze them, crash them. These are better than glass wool and rock wool. Uh, and the price, let's compare the price. Glass wool, rock wool is higher than EPS and XPS. EPS and XPS, they are cheaper than glass wool and rock wool. And we have a third group. Uh, Again, it's made out of glass, and that's called glass foam. Uh, Heat insulation, very good. Fire resistance, very good. It doesn't get burned. It's inflammable, unflammable, non-flammable. Water resistance, very good. Zero. It doesn't absorb water at all. It doesn't get damaged if you put it inside the water. Uh, Pressure resistance, very, very high. But the price is very high, of course. Let's think. We are going to use that heat insulation material to cover our foundation columns and grade beams. And once the construction is completed, we are going to put all the earth back. They will be buried inside damp earth. That means that there will be water here all around these heat insulation materials. There will be pressure of the earth and water outside these materials. So we don't need glass wool or rock wool because they will get ruined in that damp environment with the all pressuring earth. And since all these materials will be buried inside the earth, inside damp earth. Fire is a minimum risk there. There is no risk of fire. We can easily say that. So preferring uh, EPS or XPS will be a better choice. Of course, the best choice is glass foam, but since the price is very high, we can use cheap ones because they are going to be buried inside the earth and no one will see them. The only important thing is to provide a high level of heat insulation to be resistant against water damage and pressure damage. And since there is no risk of fire because they will be buried inside the damp earth, then we can prefer XPS and EPS for heat insulation of the foundations. That means that once the construction of these reinforced concrete columns and beams are completed, we can cover them with XPS boards easily. You can cut them easily with a stationary knife, and that will be all. As you remember, we created all these reinforced concrete components with waterproofing admixtures, so there's no risk of water damage. We used XPS boards for the heat insulation, and we cover the foundation columns and grade beams with these XPS boards, so we stop the heat transfer. We don't need to cover the footings and tie beams because they are under the frost line and there is no heat transfer at that level. And now we are going to put all the earth back and over the earth, compressed earth, we are placing gravel for 15 centimeters here. And over the gravel, we are going to pour concrete for 10 centimeters. Again, for that concrete, we can have waterproofing admixture. That time, the water will not go upwards through the concrete. So these are waterproofed. These are waterproofed. 10 centimeter thick concrete is waterproof. We provided the heat insulation. And there is only one thing left that we need to be careful about. It's this joint here. As you can see, there are joints in between the uh, reinforced concrete surfaces and concrete surfaces. These joints, these lines, their meeting points, uh, there can be water going upwards through these lines. And that can be a problem for us in terms of space and user. Uh, so we need to find a way in order to prevent that water leakage through those joints. Here you can see a section. It's the section that goes through here, something like that. So the grate beam has been cut and it's waterproof. So there is no water going like that upwards. There is another grate beam here. It's also waterproofed. So water cannot go inside and upwards towards the ground floor anymore. That stops there. Uh, this slab on grade concrete here in between there, it's waterproof. So the water cannot go up through that slab on grade. But their combination, their that joint between the slab on grade and reinforced concrete beams, that joint, that line, it's not waterproof. There can be gaps because these are different materials. They are created in different times. There can be gaps in between through these lines, through these joints. So we need to find a solution for that particular line. Here we have these long uh, water stop, plastic water stop. These are made out of high quality, very strong plastic material. The middle part looks like a hose, and there are wings uh, in both sides. We can use these. These are long strips. We can use these water stop to cover these joints. And this is how we can do that. Uh, when we are pouring the concrete or the reinforced concrete beams, we can place it this wing here inside the beam, and this middle part, the hose part, can be in middle, and the other wing can be placed inside the concrete slab on grade part, something like this. So that's the reinforced concrete beam. And this is the gravel. And over that, we can place the plastic water stop like that, something like this. Uh, one of its wings can be inside the reinforced concrete. As you can see, there are tiny things like uh, tongues here, so that the area of the surface will be increased and it will hold inside this concrete in a better way. And the other wing here will be placed inside the slab on grade here. When we pour the slab on grade, the concrete, it will be something like that. And over this plastic water stop here, we can have a mortar, a cement mortar with bitumen. We can fill that line, all the line, with cement mortar mixed with bitumen. Bitumen is a substance that will prevent water leakage. So there will be two solutions. The first one is this plastic water stop. So the water cannot go upwards through these joints anymore. And there is one more solution, precaution, that cement bitumen is the second precaution. If the plastic water stop gets damaged somehow, then there will be a second precaution that will hold the water. So all these things, they are now waterproof and heat insulation heat proof. It will be something like this. This will be our building, the superstructure, our columns. There will be beams and reinforced concrete floor over that. That's the structure itself. We know that each column needs to go towards inside the earth as a foundation column. And they can end with single pad footings. But we need to connect them with tie beams and connect the columns with grate beams. These are all reinforced concrete components. So we can use admixtures to create that reinforced concrete components, columns, grate beams, tie beams, and footings, so that there won't be any gaps. That means that they won't have any water inside, and the reinforcement bars, they won't be damaged. And For the heat insulation, the components above the frost line, that means that the components above the footings needs to be covered with a proper heat insulation material, and that can be EPS or XPS. We can use those boards for 5 centimeter thick to cover the 4 sides of the foundation columns and 3 sides, the outer side, the inside side, and the underside of the grate beams. We don't need to cover the footings or the tie beams because they are under the frost line and there is no heat transfer anymore. Now we can put all the earth back. That means that the excavation pit is closed now, and we see the grade level there, and the inside of the earth will be compressed. And we can place the same XPS boards over the upper surface of this compressed earth in order to provide a better heat insulation. So we cover the upper surface of the earth with these XPS boards. Now we can put 15 centimeter gravel over the XPS boards, and we can pour slab on grade concrete without reinforcement bars, but with waterproofing admixture over the gravel. Now they are at the same level, and these joints between the heat insulation, between the reinforced concrete grade beams and slab on grade, we can use plastic water stop and bitumen with concrete mortar with bitumen through these red lines, these joints, and everything will be both watertight and heat insulation will be provided. And over that, we can continue with the superstructure. But for these columns, there is no risk of water anymore. We stop the water there. There's no water, so we don't need waterproofing admixture anymore. These will be just reinforced concrete, standard concrete. And we can have the same concrete for the beams, and over the beams, we will have a 15 centimeter, 10 centimeter thick reinforced concrete floor slab integrated with the beams. This is how we do the water insulation and heat insulation in buildings without a basement floor. How can we design foundations if there is a slope on the plot area, sloping sides? This can be a small building, a one-story building, and it can be over a plot area where there is no slope, just a smooth surface. Or we can design the same building over a plot area where there are level differences, a slope on the plot. Like this side of the building, if it's 0, 0, then the other side will be plus 75. That means that this side, the upper surface of this side is 75 centimeters higher than the upper surface of the other side. How are we going to create our foundations? We need to go deep to prevent uh, frost action on the footings. Let's imagine that in that geographical location, the frost line is 80 centimeters deep from the upper surface of the earth. We need to go down for 80 centimeters. But from which side? Should I start from here and go for 80 centimeters down, or should I start from that level to go deep for 80 centimeters? Which side should I prefer? If I prefer the second side, the second alternative, then it will be something like this. I go for 80 centimeters deep and I'm going to place my footings, but on this side, the footings will be so close to the surface. That means that there is this risk of frost and expansion. And that's something we don't want. How about I go 80 centimeters from the left side also? Then how am I going to connect the footings? These will be in the upper level, these will be in the lower level, and we need to have an inclined high beam to connect them, and that's very dangerous. That shouldn't be like that. All the footings needs to be at the same level. Uh, and so that's how we can do that. We can start from this right side, go for 80 centimeters deep, and that will be the level of footings, all the footings, even if the other side needs to go more than 80 centimeters towards the inside of the earth. That will be a better solution. And since the area is sloped, when we do the excavation, there will be differences with the sloping sides of the excavation like that. And we can use higher beams to connect these different levels because of the design of our building. That part will be the ground floor will be at the 0, 0 level in this side. The ground floor will be at the plus 75 level on the other side. In order to connect all these different columns and beams together. Here we can use grade beams at normal height, but this middle part can be higher so that these columns and beams will meet together. And once we place the earth inside all these gaps, that high beam will hold the earth. It will prevent the earth to leak underneath. That's how we can do the sloping sides. For the ground floor itself, what if we don't want to use slab on grade, but we want to prefer reinforced concrete? That's in that circumstance, we can use crawl spaces. Here, in normal conditions, we put the earth back, we compress it, and then we place gravel and slab on grade on top of the earth. That's the slab on grade. But if you don't want to do that, then we can have our reinforced concrete floor directly connected to our beams, just like we did on the ceiling of the ground floor or the floor of the first floor. Something like that. And there can be a gap between the upper surface of the earth and the lower surface of the ground floor itself. On the section, it will look like that. We will have grade beams and 10 centimeter reinforced concrete floor slab for our ground floor, and there will be a gap beneath that. And that's called a crawl space, something like this. So we can construct our grade beams and we can put the earth inside, we can compress the earth and leave it like that. There will be a gap like that, and the grade beams will be constructed with the reinforced concrete floor slab integrated like this. and those empty areas will be called a crawl space. Uh, Here, as you can see, that gap can be useful for the plumbing. There will be lots of pipes, uh, and we can have space, use this space for the plumbing or wires, electric wires. And here, we need a scaffolding and forms to create that reinforced concrete floor slab. And we can leave them there like that. We don't need to take them out. They can be inside that crawl space like this, and they are called dead shores or kör kalıp in Turkish. And of course, we can have again waterproofing admixtures to create the grate beams and the floor slab, reinforced concrete floor slab, so that the reinforcement bars will be protected. And we can place our XPS boards over the form of the dead shore, and they will be there to protect the indoor ground floor, indoor heat levels. The only thing that we need to be careful about is this gap. There will be damp, humid air trapped inside the building underneath the ground floor. It will be all closed on the sides, and there is this compressed earth, and there is this humid air trapped. And that's bad. We don't want that. There can be small problems, lots of other problems. So we need air circulation. Uh, Here we can create these tiny little windows and protect them with some sort of wires, nets, so that wild animals won't go inside. And those windows will create a natural ventilation, air ventilation, so that all that trapped humid air will be swept outside. Here we see a sloped surface. There are two roads. One of them is in the 0, 0 level. The other is higher than that. When we create our building, there will be a ground floor like that, and the sides of the grade level will be sloped like this because of the sloping plot area. The section will look like that, something like this. Here, we can do our foundations like this. First, we do the excavation because of the level differences. This side will be longer and that side will be shorter, obviously. Then we are going to place our footings, single footings, one way continuous, two way continuous. We are going to do the tie beams, the foundation columns, and over these foundation columns, we can have our grate beams and the uh, reinforced concrete floor slab for the ground floor. And we can use, of course, that shores. They can be there all the time. We don't need to take them out. And we can fill the earth inside and around the building, so there is no excavation pit anymore. And we can have our little windows to provide air circulation. And if we want, we can leave the area like that, or we can change the slope. We can excavate the area like this. Then there will be a level difference between this upper road and the garden here. And there is a risk of water slide in the earth, the soil sliding towards our garden. So that's what we call a side grading. We have the same level now. There's no sloped surface on our side. And to protect the sidewalk and the road here, to prevent the earth sliding towards our building, we can have a retaining wall there. First, we excavated a little bit so that we will have enough gap to construct the retaining wall like this. We do the retaining wall, and in order to make it stronger, we can have these plasters. so that it will be stronger. And also we need to take care of the excessive water there. We need to collect the water and pass it out. Once the construction of the retaining wall is completed, we can put the earth back so that this retaining wall will be like our garden wall. Also, it will hold the pressure of this earth, soil, and it will prevent the sidewalk and the road to slide towards our building there. And if we prefer only concrete, if we don't need reinforcement bars, then we don't need to provide any waterproofing solution because there won't be any steel reinforcement bars to corrode. So that's it. That's a solution that we can do. Okay, let's now take a look at the buildings with a basement, how we can do this protection against water and heat in buildings with a basement floor. Uh, Here, as you remember, we used shear walls. There is this raft foundation or some other type of foundation and reinforced concrete floor slab. And now we have smooth surfaces, big smooth surfaces. Uh, these are all large, smooth surfaces of the shear walls, reinforced concrete shear walls, outer surfaces. And we have a smooth surface if we have a raft foundation. The beneath surface of that raft foundation is also, again, a large smooth surface. And as we excavate, let's imagine that there is water. Uh, the water table is high like that. It fills with water. Then we can use some pumps to excavate that water. And this time we need a stronger waterproofing solution. It won't be appropriate for us to prefer waterproofing admixture anymore because with the waterproofing admixture, we will be protecting the reinforcement bars of these shear walls and the floor and the raft foundation. The material, the product itself will be protected. However, if there are cracks, any type of cracks, then the water will start penetrating towards the basement floor itself. It will be dangerous for the space itself and the users. So that's why we need something stronger. Here we can prefer membranes. These are applied with blowtorch, a flame torch. In Turkish, we call it şalumo. And it's made out of bitumen. And it will be better than plaster or paint because, or the waterproofing admixture, uh, because here we know that it will be very hard for us to cover all these surfaces with membranes. It will cost a lot and there will be lots of joints, and joints means risk, water leakage risk. However, here we will have lots of smooth surfaces and the application will not be that difficult because there are fewer surfaces, large surfaces. To apply these membranes with blowtorch will be easier than applying it to a single path footing. And if the shear walls crack somehow, we know that the paint or plaster will crack with the walls as well. And those cracks will let the water be penetrated towards the basement floor. So that's something we need to avoid. However, these membranes, they are elastic. Even the concrete cracks, uh, these membranes will hold. They won't let the water pass through. They won't tear up. And these are very thin membranes. They are made out of bitumen. Bitumen is a natural substance. In some parts of the earth, you can find them on surface, and it's in this state. But mostly we gather it as a side product of petroleum as they process petroleum. in the factories, we get bitumen as the side product. And as you can see, it's not a proper material to create these sheets, membranes, so we need to modify it. There's two types of modification. We can either have oxidized bitumen, uh, that means that we can blow hot air inside the bitumen and the oxygen will have this chemical reaction. Or we can mix some thermoplastic resins inside the bitumen. Those are chemical substances. And according to the type of the resin, the final product can be plastomeric or elastomeric. Plastomeric, it has this atactic polypropylene chemical substance inside it as the thermoplastic resin, and it resists against hot weather. If you are designing a building inside in a hot climate, then you need to prefer plastomeric uh, membrane, bitumen membrane, which will include atactic polypropylene inside it, so it will hold resist against the hot weather. Or we can have elastomeric bitumen membranes. These will have stran chemical substance inside the bitumen so that it will resist against cold weather. The bitumen sheets, they are very thin. The total thickness is 4 millimeters, only 4 millimeters here, this thickness. However, it will have 5 layers. First, we have a polyethylene film. It's a transparent film to protect the bitumen layer. Then we will have either SBS modified or APP modified bitumen, either plastomeric or elastomeric modified bitumen. It's approximately 1.5 millimeters, something like that. There is another layer here as the fourth layer, and we have again polyethylene film as the finish. And in between these two bitumen layers, we have non-woven polyester or tiny wires, metal wires, or tiny plastic net. Something like this, we can create a net, a grid out of either polyester or metal or plastic here, uh, and it will work like the reinforcement bars inside the concrete floor slab. As you know, our concrete floor slab is made out of concrete, and inside that concrete, embedded inside the concrete, we have lots of reinforcement bars, so that it will become stronger against tensile strength, uh, tension stress. Uh, it will work just like that. Bitumen, 2 layers of bitumen will be combined with a polyester, metal, or uh, plastic grid net, something like tiny reinforcement net, so that it will hold, it will be very strong against tearing. And if we are going to use this bitumen sheet where it gets lots of sunlight, then this polyethylene film, it's transparent and it's very thin. It will melt away and it will harm the bitumen layer. So instead of polyethylene film, we can have fine sand as the upper surface, and then the rest will be the same. There will be a modified bitumen layer in non-woven polyester or metal net or plastic net in between. One more bitumen layer, and the last finish will be again polyethylene film. We can prefer that one, and we can place the sheet where the sand will get all the sun rays. Instead of sand, we can use granular surface. We get lots of bricks and ceramic tiles. These are broken somehow, and they are just going to be garbage. So we get them, we pulverize them, and we get lots of tiny sprinkles, and we can use them to cover the upper surface of the bitumen instead of sand. And the rest layers will be the same. Again, modified bitumen, nonwoven polyester, and polyethylene film. Or as a fourth alternative, we can have aluminum foil as the top layer so that the bitumen will be protected and this aluminum foil will reflect sun rays. So if everything will be buried inside the earth and there is no sun there, then we can prefer the first one, the one with the polyethylene film. But if one side of these bitumen sheets will be exposed to sun rays, then we can either prefer the one with the fine sand or the one with the grains of the ceramic tiles or bricks. That's granular surface layer, or the one with the aluminum foil. And we use a blowtorch and we apply them in two layers, two different layers. That means that we have this surface of shear wall or raft foundation. Now I use these have 1 meter sides. So I start applying the first one here. So it's applied. It's uh, glued with the blowtorch. As the blowtorch hits the surface of this bitumen, it melts the polyethylene film, and the upper surface of the bitumen melts a little bit, and there is a liquid bitumen on this side. It's applied with a brush so that they will melt and be glued to each other. And I'm using one more, but the sides are overlapped like this. That's the next one, so that uh, this will be looking like that. It will be under the first one, like this. And that's only for 10 centimeters. This is for only 10 centimeters, so that there won't be any water leaking at that joint. And I can do a third one next to this one, uh, again, like this. And there will be one more overlapping like that. So I cover the upper surface. I go the lower surface like that. There will be another 10 centimeter overlap, and this will be looking like that, like this. And I will cover the whole surface like this. That's the first layer. And over this first layer, I need to do a second one. I'm going to use new sheets, but this time I will be placing them like that. So the first one will be here, and the other one, again, with the overlap, it will be there. The third one will be there. As you notice, the one on the top, the joint in the lower side will be in the middle part of the one of the top. And here, these joints will be at the middle of the lower one. So it will go like this. And I will be covering the whole surface with 2 layers of bitumen. Uh, okay, so how can we do that? This is our superstructure, and that will be our ground floor. Of course, we need a gap to place our stairs or an elevator or a ramp so that the basement floor will be connected to the ground floor for the vertical circulation. In order to do the construction of the foundations, the basement floor, first we need to excavate the area and there will be just earth, damp earth, and it will be hard for the workers to work on that mud. So we can have concrete, only 10 centimeters without the reinforcement bars, and we can have these sides raised for like 50 centimeters. So it's just a surface. This is the damp earth and we don't want our workers to be on this mud. So we just pour a concrete over this damp earth for 10 centimeters. It's just like a small pool, something like this, so that they will have a smooth, clean surface. They will be away from the mud. And this will be the underside of the raft foundation. So we construct that first. And after that, we can have our bitumen sheets and we can cover the inside surface of this concrete area. But as you know, concrete has aggregates, coarse aggregates, fine aggregates, and because of these gravel, the coarse aggregates, there will be sharp corners. There can be sharp corners on the surface of the concrete. And if we place these thin membranes over these sharp corners, they will be penetrated. So this is something that we need to avoid. First, we can have one leveling concrete. That's what we call a leveling concrete. Düzeltme betonu in Turkish. For that concrete, we don't use coarse aggregate, but we just use fine aggregate, sand. With that mixture, we will have a very smooth surface. And over this surface, we can apply liquid bitumen. That's what we call a primer coating. Uh, Astar in Turkish, and it can be applied with a brush. It's just liquid bitumen. We just brush it over the surface of the leveling concrete. Now it's ready for our membranes. By using blowtorch, we can apply two layers of bitumen sheets. As you can see, they will be overlapping the first layer, and the second layer will be in the middle part. These joints will coincide with on the middle parts. There will be two layers of membrane, and we need to protect that water insulation because workers will be walking over that water insulation, and they can drop certain things. The water membranes can be damaged, so we need protection. First, we can have a separation layer, a plastic film, a very thin plastic film. And over that separation layer, we can pour concrete with fine sand again. But this time, it's not for leveling, but it's for protection. So that's how we can name it, protection concrete, koruma betonu. And now it's ready for our raft foundation. This whole horizontal surface is waterproofed, and over that protection concrete, we can create our raft foundation. Here, we have a concrete so that the workers don't walk on the mud anymore. We have a clean surface. That's concrete. It doesn't have any reinforcement bars. In Turkish, we call it grobeton. And over that, we grobeton is here. I'm sorry. Grobeton is here. That's grobeton. And over that, since there are coarse aggregates, we don't want to place our membranes. We need a surface, smooth surface. We create level and concrete. It's düzeltme betonu in Turkish. And over that, we apply primer coating. It's liquid bitumen, astar in Turkish. Uh, Over the liquid bitumen, we place our bitumen sheets, waterproofing sheets, and over that we have a separation layer, ayırıcı katman, plastic film uh, there, and over that we pour protection concrete, koruma betonu in Turkish. Now it's ready for our raft foundation, and this will be beneath our raft foundation, and this whole surface will be waterproofed. So there is no risk of water penetrating beneath the raft foundation towards the basement floor anymore. We can construct our reinforced concrete raft foundation, shear walls, and ground floor slab. The beneath is waterproof, so there is no risk of water penetration. We are going to put all the earth back, but the water can penetrate towards the sides of these shear walls. It can harm the shear walls, reinforcement bars, and it can harm the basement floor. So we need to waterproof all these surfaces as well, just like we did previously using these membranes, two layers membranes like that. But again, these are reinforced concrete shear walls, so there can be sharp edges because of the aggregate. If we just place these membranes, they can be penetrated, they can be teared. So first we can use the same mixture of sand, concrete, and water to smooth the surfaces, but this time we are not going to name it leveling concrete, but we are going to name this surface as plaster or sıva in Turkish. It will have like 1.5 or 2 centimeter thickness. Now we have a smooth surface. We can apply the liquid base, and over that we can apply our two bitumen sheets. And when we place the earth back, there can be sharp particles, sharp gravel inside the earth. Again, it can harm our membranes, so we need protection. Also, we need heat insulation as well, because as you remember, there will be a basement floor. The basement floor will be heated, and there can be heat transfer through the earth between this outside air and our basement floor, so we need heat protection. Either we can use the same plaster to protect the bitumen membranes, or we can have this drainage mat that we can use. It's a hard plastic substance to uh, direct the water towards a certain direction, or we can use our XPS boards to protect the membrane and to provide the heat insulation. So instead of this uh, plaster here in the surface, we can have our XPS boards that will protect the membranes, and they will provide heat insulation as well. This is what we need to do. We need to cover the whole outer surface of the water water insulation membranes with XPS boards. There can be another separation layer, a cardboard surface or a plastic surface to separate the water insulation from the heat insulation. Once they are covered with XPS boards, we can put the earth back, and we can continue with the superstructure like this. Uh, we know that there can be water inside the earth. If the ground is permeable, such as coarse grains like gravel or sand, then the rainwater on the surface will go towards these grains inside the lower layers. Uh, but there can be a permeable ground. There can be a layer that is not permeable, a non-permeable layer like rocks or very fine grains. That water can accumulate there like this. Or there will be a non-permeable ground, mostly fine grains like clay. They won't let the water pass through their grains. In these two circumstances, there can be water next to our footings or raft foundation. And that's something that we don't want. We want to protect the footings, the raft foundation from the water damage. If there are cracks, that water can penetrate inside the basement floor, or it can harm the reinforced concrete, reinforcement bars. If it freezes, it will expand and explode the uh, uh, components. Here we can have a perforated pipe, a drainage pipe that goes next to our footings so that all this rainwater can be collected inside that perforated pipe and drained out as a stormwater to a stormwater collection channel. Something like this. We place these pipes. These are made either out of plastic or concrete or some other material, but there are holes, tiny holes on the upper side of the pipe. Once we place the earth back, the rainwater will penetrate towards the pipe and they will go inside the pipe. Here we can use our drainage mat. These bumps will guide the rainwater to be directed towards the drainage pipe, and it will be collected inside the pipe and it will be drained out like that. Uh, Here, that's what we call a drainage system. The important thing is we need to place our pipe approximately 50 centimeters away from the outside surface of the footing, and it can be a little bit lower than the upper surface of the footing. And depending on the climatic conditions, if it rains so much, if there is so much excessive surface water, then we can prefer a larger pipe with a bigger diameter. Uh, there are options here. As you can see, there are tiny holes there. We can have different options. We can prefer the optimum one, and we can place it before we put the excavation earth back here, but the pipe won't be holding in the mid-air like this. So we can place a concrete bed first, and we can apply the pipe over the upper side of the concrete pad, and then we can put the earth back, so it will be buried inside, and all this rainwater can be collected inside this pipe. And we mostly place gravel and sand as the layers above the pipe so that the water will be filtrated. We don't want our pipe to clog down. And this white line will represent the direction of the pipe. And as the pipe gets longer and longer, it will be hard to control the water there. So we can create these catch basins or manholes, especially in the corners, in order to change direction. And if it's more than 25 meters, then we need this manhole. In Turkish, we call them rögar. It works like this. Here we have a drainage pipe, coming water incoming flow, and there is this depth. And another pipe, it's mostly lower than the first one. So the incoming water, the water can be dirty, there can be particles inside it. first fills this tank, and all the hard particles they are at the bottom now, and the water can go from the out pipe like that, and the top part needs to be movable because we need to go inside it and clean all the dirt from time to time. So that's how we can do that. Uh, the important thing is, one of the important things is provide natural light and air for our basement floors. Here we can design areaways. Since we are going to put all the excavation earth back, there is no way for us to provide natural light and natural air for our basement floors. Uh, if we place a window like that, it won't work because of the earth there. So we can create a tiny shear wall around this earth window, so that that tiny shear wall will hold the earth and water, and it can provide a clean air and natural sunlight for our basement floor, something like this. That's what we call a window well, an area well. In Turkish, we say krangles, krangles. Krangles is a French word. It means court anglais, uh, English court or something like that. And we can create an areaway as big as we want. Here, if we just need natural light, then we can close the upper surface with a semi-transparent material. We will have light, but we won't be able to get natural air this time. But if we need both air and light, then we can have an open areaway so that the air can be circulated as well. But there is a risk for users to fall down if there are people walking around the building. So we can prefer closing it with a net or a grid like this. It will allow both the air and the wind, sunlight. However, this time water will be a problem as it rains. This area will be filling with water, and we don't want it to penetrate through our window. So we need this height between the upper surface of the areaway and the water sill, window sill, and we can have a pipe. We can collect all the water in this pipe and connect it with the drainage system so that all that rainwater will be drained out uh, away from the building. The last topic, how we can protect the building from seismic activity, from earthquake activity. There are two options that we can provide. First of all, we can have movement joints. If there are differences, either because of the foundation, either because of the sloping areas, difference of levels, or either because of the weight of the building, different parts have different weight, then we can have two neighbor buildings, not just one building, but two neighbor buildings with a movement joint. And we can create two different foundations. First, we can construct that part of the foundation. As you can see, the footings are half here, and that's a complete foundation. It's finished now, and we can use XPS boards to cover these whole surfaces. And then we can start constructing the other building, the neighbor building, and there are XPS boards in between two reinforced concrete structure so that they won't be touching to each other. And that XPS board will create that movement joint, and that's a new building. If we do that, we can place them at different levels now. We don't need to provide the same level for all the footings because they are different buildings, neighbor buildings. There's a short video from Japan, a comparison of Japan and Turkey. Let's take a look.
Şu anda Tokyo'dayız. Ben burada binalar arasındaki çekme mesafelerini özellikle size göstermek istedim. Şurada daha net de görülebilir. Yani bitişik nizam diye bir şey aslına bakarsanız yok. Yani özellikle bu deprem durumundaki çekişleme etkisini sönümlendirmek için, bunun oluşmasını engellemek için diye binalar arasında mutlaka ve mutlaka bir boşluk bırakılmış. Bu şekilde derin boşluklar. Buna dilatasyon da diyemeyiz. Aslına bakarsanız çekme payları buna göre dizayn edilmiş. Hatta pencereler de var ama pencereler direkt olarak karşı binanın dibine kadar yaslanmış durumda. Bu sayede özellikle yeni ve eski binalarda, döşeme hizaları farklı olan binalarda bu çekme mesafeleri oluşturulmuş ve bitişik nizam durumundaki sakıncalı durumlar engellenmiş gözüküyor.
These are from Turkey. These examples. As you see, uh, as you see, it's very dangerous for different buildings to hit each other during the earthquake, so we need those movement joints. It will be very useful for us. And also we can have seismic isolations. There are different techniques in order to do that. They will prevent the movement of the building during the earthquake, and we can create these isolated foundation columns, or we can place these pieces of seismic isolation between the footings and the foundation columns. And that's the end of today's video. Hopefully in our next video, we are going to talk about how we can express all our decisions graphically. Okay, thanks for listening. See you soon, hopefully.